I am a associate professor at University of Washington, located at Seattle in Washington State of the United States. I'm going to introduce a micro and nanotechnology. So I want to start from a very fundamentals, and then also I want to show you how the technology is ongoing. Okay, I know there are a lot of skepticism over this field. You know, one of the main reasons for those skepticism is the device. Okay, the components made by this technology is very small. Okay, so I think through the introduction, I want to show the applications where the micro and nanotechnologies are applied. Okay, and then on Friday, I want to show you one of my examples applications in biomedical field. So today I want to go through the applications in microtechnology area, and then for tomorrow with the MEMS and then nanotechnology application area will be addressed. So regarding, if you are interested in this field over MEMS, okay, exactly speaking, that's a micro electromechanical system. It's not a simple electronics. Okay, I want to talk about the systems that has mechanical and electrical systems inside. Okay, and if you are interested in this MEMS area, then you can find very useful websites. One of them is MEMS and Nanotechnology Clearing House. Okay, so if you go to this website, then you will see a lot of material properties and then applications and devices, and plus some of job opportunities out there. And in terms of publications, one of our major journals is the Journal of MEMS, okay, and Sensors and Actuators and Lab on a Chip, and the Journal of Micromechanics and Microengineering, and plus many journals, they introduce these micro electromechanical systems. And for MEMS, you know, as far as you make small things, and then if it has electromechanical components, then we can say that's MEMS people and MEMS expertise. But sometimes you want to kind of narrow down the area, like who are the people working on MEMS area. Then we can define in this way. So MEMS means it's a device having electromechanical functions at the size of 0.1 micron through about 10 millimeter. Okay, so MEMS people, they are working at the size scale of this. Okay, and MEMS people, then, you know, of course, those are the experts working in micro electromechanical systems. And then most of those people, they are from electrical engineering and mechanical engineering and physics and chemistry, also some other engineering department. And in fact, the MEMS technology has been originated from electrical engineering. And now most of fundamental research has been done. And then, like other scientific research, most of work is conducted by mechanical engineering departments, because the problems that have to be solved is in fluidics area, and then reactions or the problems of mechanics, and all of those problems are in the area of mechanical engineering. And also, you know, they are attending a MEMS conferences. Okay, so for example, IEEE MEMS is one of the most prestigious conference among MEMS people, and also competition is kind of quite high to attend this conference. And IEEE transducers, this conference is every 2 years, and then for the years that like when this trans-use conference doesn't happen, then Hilltrade conference is held within U.S. This Hilltrade conference is held in the island of Hilltrade in I think South Carolina. Then MEMS people, they get together and discuss about their result. And also for the kind of worldwide conference, Microtips is very popular. This Microtips is micro total analysis systems. They were made among the chemistry and biomedical and electrical mechanical engineering people. And then this conference is held every year. Okay? And also, you know, since this area is really interdisciplinary area, so when we kind of want to know some of knowledge from this MEMS or nanotechnology, then I think I would recommend to use this ISI Web of Science, because somehow it gives credit, okay, for a journal. So when we are not familiar with a specific area, then this ISI Web of Science is quite helpful. And here is some of the examples. For example, if we use a keyword for example, journal source is Nature, and also the author is Izima, then he's kind of the first discoverer of nanotubes. Okay, then we can find out a lot of journals, and then one of the first journal to introduce a nanotubes, okay, it was cited for close to like 20,000 times. Okay, and typically, if this number, citation number, goes over about 5,000, then this person is kind of a nominee for a Nobel Prize. And also, you know, somehow this impact factor, I think it gives credit, okay, because review is very rigorous for the high impact journals. So when you are not familiar with some of the field, then like the good journals, they give more credit. But if you are working in a certain field, you like where you have an expertise, then you know, of course, those journals are kind of also good for that. Then let's see the market of MEMS. Okay, I got this material 2008 or 9, and then in terms of market, now it's about like 10 or 20 billion dollars per year. Okay, so it's not such a big market, but it's reasonably big. For example, when we kind of set up a company, startup company, if the market size is about like $1 billion worldwide, then it has a kind of reasonably good market for startup. Okay, and then if you think of, for example, like semiconductors, then the market size is about like a few $100 billion. Okay, and then if you go to a medicine or a biomedical area, then that's over like $1 trillion. Okay, so this one is the MEMS field is the area that is rapidly growing up. Okay, and also there is another report about the MEMS market. As you see, it shows over like $10 billion. Okay, throughout the years. Okay, so it has a market. In this area. And when I see this MEMS field, two kinds of people, they are working for this field, okay? One is the people who like the small scale technology, okay, micro scale engineering and then systems. And the other group of people is who are pursuing money, okay? And I wanna give one good example for that. So I have a friend who is working in speaker company in Illinois. They want to make a small like speakers installed in earphone or headphones. Okay, and he is fabricating micro speakers. Okay, to convert the sound into a electrical system such that it can detect or it can record, okay, the signals from there. And then in terms of scalability of the technology, okay, in one wafer, in one silicon wafer, he can fabricate about 2,500 devices. Okay, it's a kind of a magic, most fascinating part. Okay, one person can manufacture 2,500 devices in one wafer. Mm-hmm. And in one batch means he can process the wafers as a group of 25. Okay, some people, if with a larger facility, they can handle like 50 or 100. Okay, but this is a very typical number that he can process. And then each device, it was sold at DigiKey or those website, $2 each. Okay, and he's working 2 weeks, for 2 weeks in a month. Okay, of course, you know, to develop this device, he spent about 10 years. And then after that, the technology was established, and then he only needs to work for 2 weeks in a month. Okay? Of course, you know, he's a single, he is not married, so he can travel around for the remaining 2 weeks. Okay? And he takes about 10% from the sale, okay, through his technology. Then he can make $150,000 in a year. Okay? So he was kind of very happy. He was about like 2003 and 2004. And he got some of like a problem in these small speakers. Okay? There are several layers of electrodes to change the sound into electrical signals. Okay? Those small membranes, they were kind of damaged according to moisture. Okay? So when it was exposed in a very hot and humid environment, those membranes, it did not work very well. Okay? It was stuck. So all the products, they were returned. Okay? It's really, he was in panic. Okay? So he transferred to other company, but still he's okay because his interest is in MEMS technology, not in the money. Okay? But there are people who are very serious in the money rather than technology as an engineer. Then, you know, sometimes I see there's a kind of suicide and other very kind of mental problems. Okay? So if you are interested in this MEMS area, then I would strongly recommend you to go there. However, if you are interested in like money, okay, pursuing money, then this area is not a good field. Okay? Yeah. Then I want to introduce this microscale technology, and then what is different out there. Okay? So difference is kind of everywhere in small scale. Okay? Do we have any of micro scale things in our body? Do you know the diameter of a hair? It's about 60 or 70 micron. Okay? What do they do? Like, what do small hairs do in our body? Okay? If you go deeper, then the diameter of blood cells is about like 10 micron. Okay? Why is it 10 micron? And then if you see the shape of blood cells, then they are kind of elliptical shapes. It's not a perfect sphere. Okay? Why it's not a perfect sphere? Okay? What's the advantage? Okay? How they protect? They are protecting our body, right? And Also, what are the sizes of like a bacteria? It's about like 1 micron. Virus is smaller. It's about 50 nanometer or 100 nanometer. Okay. And also, if you see the blood vessel, the dimension is about tens of microns, or the thicker one is like a millimeter. Okay. Then let's see what the difference in like small scales. If you see this cantilever over there, okay, then this cantilever has a thickness of T, and then has a length of L. Okay. And then if it's a large scale, for example, like meter scale or kilometer scale, then this deflection will be very significant. Okay. So, for instance, let's see the specific case with maintaining the aspect ratio L over T as 100. Okay. If you make it a scale down, okay, then when the length is 1 micron, deflection is 1 femtometer. Okay, it's very small, right? With the same aspect ratio, when the length is 1 kilometer, then deflection is 5 kilometers, right? It will be broken by mass, right? So they are in between. And then, if we think of ourselves, then we are at the scale of 1 meter, right? So it's very hard to make ourselves as a cantilever, right? But if you think of an ant or smaller hairs, then we can make easily the cantilevers with the structures. Okay? Also, resonance frequency follows these simple mechanics. For example, in terms of bridge, their resonance frequency is 0.1 through 1 hertz, right? So they are kind of shaking by a wind. And when we think of microbeam, then the resonance frequency is 0.1 to 1 megahertz. So in atomic force microscope, we frequently use these microbeams, and then their resonance frequency 300 kilohertz or 1 megahertz. Okay. In future, when we make a nanobeams, nanoscale beams, having the length of a micron or submicron, then their resonance frequency goes up to like a gigahertz and then over 1 gigahertz. So some of semiconductors working principles have been proven through this nanoscale beam, and then they were resonated with a very high frequency. Okay. And one of the most dominant forces in microscale, that's the surface tension. Okay. Do you know what the surface tension is? What is that? Surface tension is the interfacial energy between the solution and air, right? So, for example, like we have some bubbles, right? Then they are kind of floating around. The bubble can form because of this surface tension. Without solid, okay, we can find out the interfacial energy between the solution and air. Okay, that is very dominant in small scale. What is the crossing point? That's about like 1 millimeter in terms of size scale. If you go to 1 meter, then of course mass is dominant, right? So you can swim in water, swimming pool, right? And then you can easily get out from the swimming pool, right? But some of creatures, they can't do that because the surface tension is more dominant than the mass or our power. Okay. So if you see this water strider, right, it can float. Can you float? No, right? If you float, then you will be shown up in YouTube, right? So for this water strider, it can float because mass is small, okay? And then surface tension is really dominant in this scale, okay? So if you see the legs, then they have small hairs and then they are hydrophobic, so they can easily float on water. And even its animation, okay? If you see these two ends, and this one is kind of trapped inside a small solution, right? Why is that? In this small drop, in the small scale, the pressure is increasing with the decrease of the diameter of the drop. Okay? So inside the pressure is really large, so this end doesn't have enough power to break off this surface tension. Okay? And if you getting kind of smaller, like micron and sub-micron scale, and of course capillary action and surface tension, they are really dominant. Okay? So we are spending a lot of time to understand this surface tension and capillary action. Sometimes, they are really kind of big barrier to overcome in the manufacturing process. But sometimes we can utilize this capillary action to fabricate such a devices. Okay. Then, I want to show you a few processes for microfabrication. This microfabrication process has been developed by the semiconductor people. So they made the semiconductors, and then at a certain point they discovered a new method to manufacture three-dimensional structures. Okay? It's not a simple two-dimensional. Okay? These, if you see the original process, then the silicon, pure silicon, is melt in a kind of hot pot, and then they are forming a crystals. And then after forming crystals, those crystallized structures, they are diced into a wafer. Okay? So it's a single crystal silicon, and then we know the orientation of those single crystals. Okay? And then the next typical step is oxidation. So we have a silicon wafer, okay, then it can be oxidized very easily with the reaction of oxygen in air. Okay? However, if we put them in a very hot furnace, its temperature is like 1,000 Celsius degree, and then if we give oxygen in the chamber, then those wafers will be oxidized. Okay? Silicon is a representative semiconductor material. Silicon dioxide, that's the insulation layer. Okay? So those two materials, they are very frequently used in the MEMS process. And then after that, we are using some of like a pattern to transfer a pattern to a wafer. Okay? This process is called a lithography step. Okay? And then through the etching and deposition, we can make various devices, and then those devices, they are diced with individual chips, and then they are packaged. Right? These electronic chips, they are installed in these laptops and then everywhere. In the similar way, also MEMS chips, they are packaged and then installed in devices. Okay? That's why we can see these MEMS devices in our world. Okay? I want to go through some of MEMS process like lithography, and then metal deposition, oxidation, and then deposition and etching. Those 5 processes are most kind of fundamental steps for this MEMS technology. Okay? And for the lithography, is the step to transfer a pattern from a mask, okay, to a wafer. Okay? For example, we have a silicon wafer, and then silicon wafer has an oxide layer on top. Okay? Then we can coat a photoresist. Resist means it's very sensitive to a light. Okay, so if you go to a lithography room, then there is like a specific filter. So this resist is sensitive to UV light, but UV light is not present in the room. Okay? And then once resist is coated on top, then we can use a mask that has a specific pattern. For this case, this area is a blank. Okay? And then the other area is covered with a metal layer. Okay? Then when we expose light, UV light on top, this area, light can penetrate, and then this dark area, light cannot pass through. Then polymer can be, those kind of polymer chains can be broken on the exposed area. Okay? However, on the exposed area, the polymer chains will not be broken. Okay? I suppose specific, some of polymers, they are hardened under the exposure. That's called a negative photoresist. Okay? If the exposed area is broken, then it's called a positive resist. So we can kind of switch the pattern. Then finally, those photoresist polymer can be used as a mask to etch out silicon oxide. So if you put this vapor into a hydrofluoric acid, then that will etch out a silicon oxide, but it does not etch the photoresist. Then in that way, we can find out the pattern. We can transfer the pattern from the mask to the final silicon vapor. So this process that has included the growth of a film, oxidation film, and then lithography steps, and then through the etching, we can transfer this square pattern onto a final silicon vapor. And this machine is a lithography machine, it's called MA6. So UV light that's exposed onto vapor, and then pattern is transferred onto that. Then we can expose the pattern onto light, and then using the pattern, we can etch out oxidation layer. Okay. And in terms of UV light, there are various lengths of UV light. So when we use a halogen lamp, then we can see a lot of lights, and then using a filter, we can filter out like a specific line, for example, I line or H line or G line. Then that means it's a G line is a 436 nanometer. Okay. Then when we want a pattern using like a G line, then about 2 micrometer patterns can be obtained using this G line. And then if we make this wavelength very small, like 10 nanometer, then we can have a pattern about like 20 nanometer. Okay? And this one is kind of an old graph. It's shown in like 1999. And then at that time, they predicted the wavelength sources. Okay? So those conventional UV light is here. It's about like a 400 nanometer. It was scaled down to 250 nanometer and 180, and then wavelength now becomes 13.4 nanometer. Okay, so using this extreme UV light, these days about 17 nanometer patterns they are made. Okay? That's the current state of the art. The interesting thing was, for example, like one company made a success in fabricating 100 nanometer pattern. Then within like 6 months, the other company they follow up. Okay, and then that trend was continued until like 50 nanometer, and then they got down to 40 nanometer patterns, okay? And then from the 40 nanometer down to 20 nanometer, only 2 or 3 companies they can make a product. And also the yield was different. Yield of this semiconductor fabrication in a very small scale, it should be over 70%. Then it's commercially viable. If it's less than 70%, even though I can make some patterns, those devices cannot be produced because of the high manufacturing cost. So now semiconductor companies, they are competing with this small wavelength. And another process is summer oxidation. So we have a silicon wafer, then we use this kind of chambers. Okay? In the chamber, the temperature goes up to about like 1,000 Celsius degree, and then silicon vapor that's oxidized, then we can get amorphous silicon oxide layer. Okay? So for this silicon oxide, it's kind of close to the window glass, okay? But it's more pure and then clean structure. And then of course, you know, it's a insulation layer. And of course, you know, if you want to have some patterns on the wafer surface, then chemical vapor deposition is very frequently used. This chemical vapor deposition process now is very popular to make solar cells. Okay? Solar cell is made of polysilicon. Okay? And then using this chemical vapor deposition, we can make silicon nitride oxide layers or polysilicon layers or other semiconductor films. Okay? We can make a lot of those films. And then the good thing for this process is a temperature, lower temperature. Temperature is typically operating temperature is 700 Celsius degree. It's lower than summer oxide. So when we compare the oxidation layer made by chemical vapor deposition and also summer oxidation, the oxide layer from this chemical vapor deposition is kind of less dense. However, it can use lower temperature, so some of the metal layer like chromium is safe in this process. Okay? And these structures, they are used as a structural layer. And if you see the chamber, then the vacuum is kind of is a little bit high in the process. It's about like 300 milliliter. And then in this vacuum, we can make a plasma, and then a plasma will generate a lot of ions. Those ions will react on the surface, and film can be very uniformly formed. Okay? So key thing for this chemical vapor deposition is to make a very uniform layer. So creation of a laminar flow, okay, on the surface, and then make a very stable reaction on the surface. That's very critical for this chemical vapor deposition. And also metal deposition is being made by this physical vapor deposition process. So you know, it's very simple. We make a very high vacuum, for example, 10 to minus 6 or 10 to minus 7 torr, okay? And then in a high vacuum, we generate a lot of heat for a material. If you put a gold inside, then in this high vacuum, with the heat, and those materials can be evaporated. Basically, you know, in this high vacuum, all the things, all the materials, they can be evaporated. Okay? So, for example, like if you put a mouse, like this kind of things in there, it's very easily evaporated. Right? So now these days, people like they try to evaporate like DNA or other biomolecules or physical particles. They can be evaporated through the in a high vacuum chamber. The good thing for this high vacuum is a mean free path is very long. Okay? So we can make a very uniform film on the surface. Okay? And then those thickness variation of the layer is exactly matching with the analytical equations. So it's very frequently used for deposition. So this is a working principle. We have some of material here, and then we generate electrons from the tungsten film, and then those electrons are guided by magnet, and then they are evaporated in the chamber. Then, of course, if we put like a flat wafer, then in the center, the thickness will be the largest because the flux of the material is the highest. And then if you go to the edge of the wafer, then it will be smaller. In order to have a uniform thickness of layers, we use this kind of a planetary system. So we can install the wafers in this planetary. And then during the evaporation, this planetary is kind of rotating. Okay? So we can have a very uniform coating of aluminum, titanium, chromium, gold, and all other materials can be deposited. And once we deposit some of materials, then of course we need to etch the materials in order to make a patterns. Okay? So if you see the etching, then there are two kinds of methods. One is a wet etching, and the other is a gas-based etching. For example, like you wash your hands with a soap, right? Then that's a kind of an etching process to etch out all the germs on your hands, right? In a similar way, when we put the wafers etching out silicon, not silicon oxide, then silicon can be etched in an isotropic way or anisotropic way. Okay? So that's a wet etching. And gas-based etching, that's typically involve the environment of plasma. Okay? So we make a small vacuum, and then plasma is generated by an electric field, and then those plasma environment is used to etch out some of materials. Okay? So this plasma is frequently used in this MEMS process. So we shortly went over the processes in MEMS. The first one was lithography, and then second one was thermal oxidation, and third one was chemical vapor deposition, and then the fourth one was a physical vapor deposition, and the final one was wet and dry etching. Okay. Then let's make a simple device, okay, like a cantilever. A cantilever is very frequently used as probes or sensors or actuators. For example, I have a mask, looks like that. So it has two square platforms, and then I want to make a cantilever, looks like that. Then in two-dimensional glass, I can make a pattern made of chromium materials. Then this transparent area, UV light can penetrate, and dark area, UV light cannot go there. Okay? So I want to use this mask as a tool to fabricate a cantilevers. Then we start from the silicon wafer, and silicon nitride layer can be deposited. So silicon nitride is an insulation material, and structurally it's very robust. So it's a good material for fabrication. Okay. And then we can coat another metal layer, aluminum layer on top. That's the green layer. Okay. So now we are seeing the cross section of a wafer. So in MEMS structure, sometimes we need to actuate the cantilevers. Then there are various mechanisms for actuation, and then one of them is electrostatic actuation. It's simple. We apply electric potential like 100 volt. Then by the electrostatic attraction, we can actuate the cantilevers. That's why we deposited metal layer on top. And we will spin coat a photoresist because we want to transfer this pattern onto silicon wafers. Okay. Then, if we use a lithography, then this pattern can be transferred onto a photoresist. Then you will see the small gap. That is the gap of this area. So now we are seeing the cross section over there. Okay. So a small gap was transferred onto this polymer layer, then we can use this polymer layer as the mask to etch out the green aluminum layer. Okay? So pattern was transferred to this aluminum layer. Then again, the aluminum can be used to protect silicon nitride, and then this silicon nitride layer will be etched out by a gas phase etching method. Then finally, we will use some of isotropic etching method to etch out a silicons. Then with this isotropic etching method, undercut will be created out there. Then cantilever will be suspended, and then these two structure will remain, okay, as a junction. Then this is a structure that we can fabricate. So if you see this structure, then you will see the white area. When we take electron microscope for a structure, white area means more of electron charge is electron is charged accumulated at the edge. So the area is looks like very white. Yeah.
You don't have problems with internal stress in this way of fabrication?
Yeah, that's right. That's a good question. So the most difficult thing, challenging thing is the control of the internal structure. Residual stress is present for this, for example, silicon nitride layer. That's the tensional stress is present. And then for this aluminum layer, usually that has a compressive stress present. So if you see this cantilever, it was kind of bent up, right? That's because of the residual stress. So we have to control those in order to match the stress in the cantilever, okay, through the fabrication steps. That's a very challenging problem. So I have described all the procedure to fabricate this cantilever. However, when you do the process with the fabrication equipment in your university, then you will see different structures. Okay? So even though all the procedures they are exposed and patented, it cannot be easily copied. Okay? That's a kind of a very important issue that was raised. Anyway, then this dark structure is it's a silicon structure, and then a white structure there's undercut. So this structure can be completely suspended in air, and when you apply electric potential to the bottom silicon layer and then top aluminum layer, it can be actuated by the electric potential. You have to apply a lot of voltage when you really operate this structure. About like 100 volt or 200 volt should be applied to make the structure actuation. Okay. Then using those processes, MEMS processes, we can do a lot of things. Okay? And the first area of applications was sensors and actuators. The first device that was made through this MEMS, it was a pressure sensor. Okay? If you see a lot of industrial applications, it has small sensors. That's the pressure sensor. And the second one was accelerometer. Okay, accelerometer. If we think of like 1990s or 1980s, there were accelerometers, but it was very expensive, like $1,000, or a more precise one was $10,000. Okay. Using the MEMS technology, now the accelerometer that we can purchase from the analog device or semiconductor companies is about like $3 or $2. Okay. Price was reduced a lot. Okay. And the second area is biomems. This area is coupled with micro scale and nanoscale fluidics. And then a lot of people in mechanical engineering, they are investigating this micro and nano fluidics. This micro nano fluidics, it was initiated 1980s. And then if you see one university in US, then about 500 to 1,000 groups, they are playing with the microfluidics. Okay? But it was not such a successful, okay, until now. And then even like in the very recent years, universities in US, they do not make a patent using this microfluidics. But very recently, within like 2 years, some of companies, a few companies, they are started to making a product in biosensors or medicine or those. And then their profit is really huge. So they ran a very high risk in the field, and then they are gaining a lot of profits from them. Okay. And the third one is optical MEMS. So if you see the optical MEMS, then those chips, MEMS chips, they are installed in the beam projector. Okay, so in the projector, about 1,000 by 1,000 arrays of micrometers, they are installed out there, and then those individual meters, they are individually controlled to reflect 3 colors, RGB colors, and then through the combination, they can make a unique color. Okay? So if you see the screen, then you will see the kind of gaps between the meters. Okay, you want to check to see? Come here. Yeah. What's your name? Matt. Okay. Come here. Can you see the small squares? You see the grids? Yeah, that's right. Oh, what's the size of grids? Okay, the size of grids is about like a few millimeters. And if you see those grids, then width is about like a millimeter. Okay, but in the chip, the width is about 4 micron. Okay, so 4 micron was amplified to be about like a millimeter. And when we see the whole picture, okay, then we can see the colors through the combination of those RGB colors. It's kind of amazing, one of the MEMS products. If you think of like 10 years ago, then this projector, it was very color was very timid, and then it was very expensive. It was about $10,000 and more. Now the cheap one of this beam projector is only like $500, right? And then one projector that has 3 chips, okay, that are made by Texas Instruments, and then one chip costs about $150. Okay, out of $500, 3 chips are $450, right? Then $50 goes to manufacturer, and then $450 goes to the Texas Instrument. Okay. Anyway, those kind of innovations, revolutions were made for these optical MEMS, and then still it's ongoing through various products. And RF MEMS, this one is one of our representative one is switch. Okay, if you see your cell phone, it can get the signal through the radio frequency. Okay, and then the switching is done by this MEMS product. Okay, this MEMS product is, in this sense, is everywhere. Just it's very hard to see where they are because they are hidden in the device. Okay. And also packaging and material characterization and cell particle handling. Also, this area is coupled with BioMEMS, and then NEMS is a nanoscale electromechanical systems, but none of the products has been shown yet. Okay. For this NEMS, when you think of a MEMS product, it took about 10 years to 30 years of incubation time to set up a fabrication process with a very high yield. For example, like when a students they are working on this MEMS process, the yield is about like 10 or 20%, sometimes like 50%. Okay? If the yield of the process is over 15%, then through the experts in these MEMS companies, it can be commercialized as the perfect yield. Okay? Then I want to go through the application area, okay, of this. So the first part was the sensors and actuators. I want to give you various examples of these MEMS. This sensor is working as an electrostatic actuation. So this area is kind of static. Okay, this area does not move. It's kind of a junction, and then this part is floating. Okay, and when we apply electric potential between, okay, then electrostatic force is working through here, and then the force is same, equal for these two gaps. Then this one will be attracted to this junction. Okay? So this moving part can be attracted. And then when you remove this voltage, then it's recovered by elastic energy. So when we apply electric potential in between, then this electrostatic energy that will pull in this cantilever, and when we remove the electric potential, then it will be recovered by elastic energy. So this one, the advantage of MEMS is that we can make many, okay, of these. When we make one, then we can create about 20 nanonewton. It's a very small force. But we can make 1,000 or 10,000 or million of them. Then we can create micronewton very easily. Okay? So this is a COM drive. Okay? So if you see this structure, then the center one, that's the elastic beam, okay, that is suspended. And then this structure and this structure, that comes with a COM drive. Okay? A lot of cantilever fingers, they are kind of interfaced out there. And when we apply electric potential of this structure and then this structure, then this cantilever beam will be attracted to this side. Okay? And then if we remove the potential in between, then it will return to the original position by elastic energy. Okay? So this is the kind of zoomed in view of those COM drive structures. Yeah, let's see some of a COM drive actuator. So this is a structure that I have fabricated with my colleague when I was a student. And then COM drive actuator is on this side, and then it was attracted to this way. And there is a hinge out there. So we want to install a kind of cantilever, like nano wires in there. And then when the structure is kind of released, we want to measure the elasticity of a structure. Okay? So this device, it was further developed to make a very precise kind of instrument tension test meter. So we have two probes, and then nano wire, it was installed on top. Okay? And welding was done on both parts. Okay, welding, the method itself is quite much different from the welding, large manufacturing. But we can use a thermopolymer and then burn out the polymer on top to make a soldering on the surface. Then it will hold the structure, and then it was by a spring. It was under tensile stress. Then we can see the stress and strain curve with the. Then we can find out the Young's modulus of the structure. So it's a kind of instrument to get the modulus, elastic modulus of the structure. And if you see the map structure, then you will see a lot of rotating or linear motions. And you will see a very familiar object out there. And one of them is this inkjet printer. Okay, so in the inkjet printer, there's like a small nozzle, and then we can heat up the solution. Then it will be shoot to the structure. Then they will make a pattern, and that's an inkjet printer. And this process shows MEMS kind of process. So it gives a lot of structures and then also actuation. Then this actuation is coupled with the meters, and then that's optical MEMS. If it's coupled with the sensors, then that's physical sensors or biochemical sensors. Okay? Mm-hmm. And you just like quickly saw a one picture showing the inkjet cleaner. If you see the early version, then there's like a small chamber. Okay, in the chamber, solution can be transferred by capillary action. Capillary is so strong such that it can transport the solution to a chamber. And then there is a heater on top. So if we increase the heat temperature, then that will expand the solution inside, and then it will be shot through the nozzle. Then this small drop will be a pattern on a paper, and that's printing. Okay, and the interesting thing is this speed for a boiling. Okay, we need just 1 microsecond to boil up a solution because the volume of the solution is only a 10 picoliter. That's the advantage of this small scale technology. And then ejection speed is really high. And for the previous like 20 years, we got a lot of advantage from this inkjet printer. And now this inkjet printer is being used to pattern 3-dimensional structures. Okay? So if you have a 3D printer, this is 3D printer is only costs about like $2,000, or expensive one is like $20,000. We can put a lot of materials, starting from, for example, like a metal particles, or like a nanotubes or nanomaterials. Or sometimes I saw they put some of like fruits, okay, ground fruits inside. Then they can make a food with that. But it's a 3-dimensional structure. It's formed through this inkjet printer. So it's gaining more popularity. And this actuator, working principle is very simple. We have this cantilever structure, okay, and then the thickness of this one is very low compared with the other arm. Then when we apply electric potential, this area will be very hot, and then this area relatively cold. Then deflection will happen through this way. Okay? And then good thing for this MEMS is once we have an idea, then that will be can be easily calculated through the ANSYS or other simulation softwares. And then of course there are a lot of MEMS companies. They can make it for you. Okay? So this is an actuator. And one of the successful areas is this accelerometer. Okay? Using a capacitance measurement, we can easily detect the motion, okay, in 3-dimension or rotation. Okay? Gyrometer can be easily fabricated. So this one chip is only like $1 or $2. More precise one is about like $5. Okay? So we can have a lot of make a lot of sensors out there, and yeah, they made us this kind of video clips. If you see, then depending on the frequency, they measured the deflection over those acceleration of a chip. Then they can analyze the signal from there. Okay. And in commercial applications, I think the cars, they got lots of advantage. Airbags, they detect the motion of high gravity acceleration. Then we can make these airbags inflated, okay, at the right time of the moment. And also GPS, gyros, and the signals, they are received and then actuated through the MEMS device in a car. You know, originally these like a GPS was really expensive, but it's getting cheaper and cheaper, and now it's installed in a very like low-cost cars. And a lot of game machines like a Wii or Xbox or those, all of them, they are coupled with detection of motions, right? Rotational motion or XYZ motion. So all of them, they are installed in this small remote controller. Okay? And if you see the pressure sensor, then we can make a very thin membrane using a silicon layer. Then we can measure the resistance change, and then this membrane, when it is inflated, then we can detect them on the surface. And this one of those sensors, they are installed in the pressure monitoring system, so we can check the pressure on a tire, okay, or all of those. But I guess maybe like 1 out of 100 or 1 out of 1,000 or 10,000, only those products were commercialized. Okay, they are having a lot of research fund like spent on these, and then one of these, the project was this high-speed rotor. Okay, they in MIT they designed a rotor to run this like a blaze with a speed of 2.4 million RPM, and then at the beginning, initiation of this project, about a few $100 million were spent, and then hope to see the rotation of this blade, but manufacturing was not enough to realize small blades, and then it was kind of easily broken, okay, during the rotation. So it was not successfully done. Okay. However, these like a small scale valves and things they all made, and now a lot of communications among these valves, okay, or network, and then through motion, they are being studied. Okay. I think some of them they are for military purposes, and some of them medical purposes they are being used. Okay. And the second area is biomems. Okay. Biochips are one of the major motivation for this MEMS process. So if you see these biomems, then technically, we, in order to detect DNA in our body, there are a lot of multiple steps of experimental procedures. They can be integrated into a single chip, okay, over here. So, for instance, we have a blood out there. Then, blood has a lot of cells and DNA, or like a bacteria or other like entities in there, and then they will be separated in microfluidics channels. Okay. And in this chamber, we can apply the pressure to mix specific reagent or sort some of particles that we want. And once we separate the particles that we want, then we can extract DNA from there. And then heater will be installed at the final stage to amplify the number of copies of DNA in there. Okay. Then originally it was it needs a very huge lab, but now in a small chip, like it's the size of my hand, that can be used to see what kind of DNA is in there. Okay. Now the price of one chip is about like $100. It's not cheap, okay? But it's being made through the nanofluidics at this moment. And then, for example, in order to analyze a genome of individual, it was about $1 million per person, okay? About 10 years ago. And through the application of this technology, now it's about $100,000, and then final goal is $1,000. Okay? So that's the goal of this huge project. Then ultimately all the individuals will have the information of individual genes. Then advantage is we can have a statistics, okay, of those genes and then diseases. Then we can couple them. Then once we know our genes, then we know what kind of diseases we will go through our life. Okay? That's an advantage, and also it can be a disadvantage. Okay, we don't need to know all of them. Yeah. And this one is also innovation of idea. Okay, in MEMS technology, we have a small cantilever. Okay, and then on the surface of this cantilever, pro-molecules, they are bound. Okay? For example, antibodies. Then, when these cantilevers are exposed in certain situation, in air or in solution, then bacterial cells or viruses, they are bound onto that. Then, this cantilever will be deflected by the interaction of these molecules. So surface stress is changed. Then deflection can be measured to see whether we have a specific target or not. So it has been tried for disease diagnosis. Okay? And then it was investigated for about 15 years, but it failed. Because under this cantilever, a bubble formed. Okay? Then capillary action, that was really dominant on the deflection over this cantilever. So it was not successful, but it has been studied for about like 15 years. And if you see this structure, then they are mimicking the eyes of insect. Okay? So if you see the eyes of insect, then they can technically see about like 180 degree, because they have a lot of cells on the eyeball, and then it was made with a polymer structure. Okay? So through the development of fabrication method for polymer fabrication, they made this spherical structure. So technically, they can see about 180 degree area around these eyeballs. Okay? And also, artificial skin, it was very popular to make it. So if you see your skin, then it's really sensitive to temperature, right? You can detect temperature, and also when you kind of press it, you can feel the pressure, right? And also, if there's scratch, then it's bleeding, then through the coagulation, it can protect, right, the skin surface. All of those functions, they are being made through the this fabrication of artificial skin. Okay, so that's one of a very popular area. And also these small probes, they were made to collect a small volume of solutions. Okay, if you think of a mosquito, then they have like a small needle, right? And then it will probe into through your skin, and then they will collect, right? Steal your blood, right? But you do not feel that much because it's small, right? So these small chips, they are made for detection of glucose or bacterial pathogens in our blood. For instance, for diabetic patients, they need to see continuously see the glucose level in blood. So they have to use some of like a finger prick test. Then it's really painful. They need to do that for about 7 times in a day. But using this, we can continuously collect blood without pain, okay? Or intermittently, we can collect the blood through this. So we can use this for the gene and drug delivery and disease diagnosis. And some of BioMEMS area, they are utilizing an insect. Okay? So this cockroach is installed with these MEMS chips, and then it's controlled by the remote control. So we can make this cockroach move forward or backward or like like stays through the signal, electric signal on top. And you know, I think about 5 years ago there was a project from DARPA in U.S. They wanted to control a mouse to deliver like a specific agent, or it's for a military purpose. And then, so they investigate the mouse from the larva stage till the fully matured mouse. And then the project itself was successful, and then they could control the mouse. The problem was when they released it in a desert area, if it's too hot or too cold, then it did not move at all, even though we give electric signal. So technically, it's not being used, but it was possible to control these insects. Okay? And then I have some of our video clips to show the separation of particles or fluid. So this red and then green ink, they can be controlled, separated by the pressure. Okay? And then if you see some of them, then they can be made as a small drop, and also we can mix the green with the red solution. Okay? So this sorting, separation, and transport, and then mixing, that's the basic technology for this microfluidics and MEMS. And this approach, it was initiated by Duke University. They can make a small drop of a solution by controlling the surface tension using an electric field. So they can make a kind of a digital droplets out there, and then they are individually controlled to make biochips. Okay? So initially, it was like a really dexterous to manipulate small droplets. And then there is a product from Philips. Philips, they made a liquid book. So it's like color, and it's colorless, like a black and white screen. And then they made a book with this liquid handling technology. And then they applied this to biochips, but it was not such a successful, because in blood there are lots of ions inside, so that was not compatible with an electric field. And you know, this gene export system is a very recent product. It was commercialized within a few years, and then they are making a very big revenue. It was this microfluidic device. It was initiated 1991, and then incubation process was about 20 years. Now we have a product out there. So to know what kind of disease you have, it took about like a few days. But with this product, now it takes about 2 hours. That's an innovation. But in order to see a disease within like 30 minutes or less than that, we need more innovation in this field. Then you know, ultimately, what we are going to do with that, right? I'm not quite sure if you know this person. Okay, it's a 6 million man. Okay. It's kind of this kind of artificial human being, okay, or humanoid robots. Okay. Now I think individual components, for example, like fingers and skins and nose, and then tongue, okay, or eyes, hairs, all of them, they were individually made. Okay. And then in future, I think those actuators and sensors and individual components, they will be assembled to make this kind of robots and also devices to help ourselves. Okay? Yeah, I want to kind of stop at this point and then continue tomorrow. Do you have any questions? about MEMS device? Okay, thank you.